record button. Last time we saw the Chow-Net's criteria. So purpose of Chow-Net's criteria is to reject the doubtful readings. Okay, you cannot just reject the reading, but you have to reject based on the statistics. Okay, so this table I will share you. I will skip some values, but I will give the full table to you. There is also curve. From that we can read the value. Okay. So we also saw one problem, and in that problem we rejected one value because it was more than d max by sigma value. Okay. Then again we calculated the value. Again we find. So we can go on repeating this. Okay. Still we reject all the readings. Okay. So once we reject that reading, so what benefit you actually get is your value of sigma will get reduced. Okay. So because sigma will give ultimately the error. Okay. The error get reduced means you get more confidence on your experiments. Okay. Now today we will see the Z test for testing the hypothesis. Okay, Z test for testing the hypothesis. Okay, I'll just take screenshot. Okay, so there is a formula for this. So the formula is Z for the sample is equals to X mean for the sample minus mu H0, that is we call it as a null hypothesis, that is the mean of the population. Okay, divided by standard deviation of population divided by square root of n, where n is the number of sample, number of reading, yeah, observation in the sample. Okay, sometimes you may be interested whether the sample is representing the population. Okay, in that case we can do this calculation. Okay, so mu h0 is a hypothesis, that is a null hypothesis for the population. Now we'll move further and we'll see one problem. Okay, so please understand this is a very large topic and we cannot take each and everything, so we just touch the topic and go. Okay, now before that I have created this table already. Okay, but what happens in the problem, they will give level of confidence, level of significance. Okay, from that we have to, from the table you need to find what is the range of Z. Okay, now if you want level of significance 5%, if you want level of significance 5%, your Z value will change from, your Z value will change from your Z value will change from minus 1.96 to the plus 9.6. Okay, the problem they will say level of significance. Now for 5% level of significance, it is a minus 1.96 to the plus 1.96. If they want 10% level of significance, then value of Z is minus 1.65 to the plus 1.65. Okay, even you can derive it from the table. Okay, already I have given the table of the Z value. From that you can derive. Okay, you can derive from the table. Okay, so I will just read the problem. There is a sample of 400 male student. So It is about sample. Sample where n in the sample is 400. And mean of sample, okay? Mean of sample, I would denote it as a x bar here in the equation. So it is 67.47 inch. Please understand, you need to distinguish between the sample and population. Okay, this is a sample. Now it is asked, can we reasonably regard this sample from the population where the mean height is 67.39 inches, standard deviation is 1.3 inches, and we need to test this at 5% level of significance. When in the question it is asked 5% level of significance means it is a 1.96. Z is plus minus 1.96. Okay, minus 1.96 to plus 1.96. When it is said 10% level of significance means it will be 1.65, I think. No? Can anyone remember what was the value for 10% level of significance? Yes. What was the
minus
value?
1.6.
1.65. Just yeah, 1 point plus minus 1.65. Okay, so we have to remember that. Okay, so you first write the values. First you write for sample. So for sample, what is given? N is given 400 and x bar is given
67.47.
67.47. Okay, now for population, it is given mean is given.
67.7.
So that mean we'll call it as what? Hypothesis. And that is null hypothesis. So it is mu h0 is given.
67.39.
67.39. And standard deviation is given. So we call it as a population standard deviation. 1.36 inches. And 5% level means what? We have to write then Z is equals to, I will say Z of population is equals to 1.96 plus minus
1.96.
plus minus 1.96. Okay. So if you put the values, you can calculate Z for the population, Z for the sample. Okay. So you just do that. First, what is given, you have to identify. Once you write whatever is given in terms of the variable like n, x bar, mu h0, that is null hypothesis, sigma of population, then ZP 5% level of significance, then you have to understand from Z table that it is a 1.96 plus minus. Now you put in the equation Z is equals to x bar minus mu h0 divided by sigma p divided by square root of n. So you substitute the value, you will get the value of ZP. So you got the value of Z. Now your spread is what? For population 1.962 1.96 minus 1.962 plus 1.96. Now your value of Z is coming. It is coming around
1.2.
1.23. So obvious that it is right. It is inside this range. Okay. So we can conclude that as Z is less than Z of population Hence, we can say that the sample is within the population. Okay, that we conclusion we can draw. Okay, this will solve this problem. Okay. Now next problem, we'll see how many readings we need to take for having variation in the mean reading. Like the problem it is given that we want to have a variation in the mean, we can say mean value plus minus 0.2%, but our accuracy of our instrument is 0.5 mm. Okay, and we want 5% level of significance. What is 5% level of significance means? We want 5% chances that reading will not lie in that range. Okay, so again here the value of Z will be plus minus, that is 1.96. Okay, so we'll just see the formula how to solve this. Okay, so the formula is how to find this plus minus 0.2 mm is Z into sigma, okay, divided by square root of n, when n is the number of readings. So it is asked how many number of readings is needed to bound our variation in the reading, mean reading. What they are asked, variation in mean reading to be 0.2 mm. So the formula is Z divided by standard deviation. Standard deviation for what? Population. So population standard deviation is a 0.5 and divided by square root of n. Okay. So please understand here, when we go from the when we go from sample, when we go from population to sample, what we do? We divide sigma population, means we say sigma population by square root of n. N is number of reading, is equals to sigma for sample, in short. Okay, because plus minus this value is nothing but what? Z into sigma. Okay, this value is nothing but variation is nothing but Z into sigma. So sigma for, in short, sample is what? Sigma p divided by square root of n. N is the number of readings. Okay, in this way we do. So we put the values now. We put the Z for 5% level of significance. It is 1.96, and if you see the standard deviation, it is 0.5 mm divided by square root number of readings. Now we know how much variation we want plus minus in mean reading. It is 0.2 mm. So we can find n to be 24.01. Now to take nearest higher value, so it comes to be 25%. So we can maintain now our mean reading as x plus minus.
Sir, how you got 0.2 mm?
Yes, it is
How
given
you got
in the
0?
problem. It is given 0.2 mm is given in the problem. I will just show you the problem. It is asked in the problem to maintain up to this value. See,
Yes, yes.
we have to design in
I
such way that it is plus minus 0.2. So how many
yes,
readings
okay.
you need? Okay. So this was about you can say hypothesis testing. Okay, we also saw a little bit statistics because to understand that we need the statistics. Now we'll go for error analysis. For that, I will just share the another slide. I will stop sharing now. Now I will go to the other slide. It's not showing anything. Okay. Go to the other PPT. Okay. I'll open the PPT. I think it was showing. I'll open it. Please understand, error analysis is a very important aspect of the research, and you need to mention that what is your error in the measurement. Okay, what is your error in the measurement? So I will take the error and error analysis. Speaking. Are you able to see the screen?
Yes.
Yes. But it's showing
Yes, sir.
error and error analysis, no?
Error and error analysis.
So here, this thing paused. Okay, just I will check. Hmm. So I will again reshare. Stop sharing. So we are seeing the error and error analysis. So when we measure anything, there is always error. There is always error. So what is the error? What is mean by error? Error is a true value minus measured value. So error is what? True value minus measured value.
Major value.
Yeah. So I'm getting some problem with sharing. Okay, it is a difference between true value or actual value and measured value. That is called as the error analysis. So as I mentioned, it is required by many journals to specify the measurement error. And if you specify that your measurement error is 10%, 15%, so probably they will not accept your research because the error is too high to believe your data. Okay. So what we need to do is to study before going for experiments. We need to study whether our measurement or measuring instrument will give the required accuracy. Okay. When we go for designing this experiment, then we need to when we go for designing the experiments, our aim will be to minimize the error so that whatever our readings data obtained will be believable. Okay, if the error is too high in measurement, and we specify, because we need to specify the truth. Okay, so if your error is 15% and if you write 5%, so you are away from the truth and we are misleading the readers of your research paper. So we have to avoid that. So right from the beginning, when we choose the instruments for measurement, we need to try, first you need to try to minimize the error. Okay. Please understand, I can only control anything if I measure it. Okay, so I need to measure and then I can control. Okay, so measurement is very important. Okay, for controlling anything. Okay, so we'll see first what are the major categories of error. There are two major categories of error. First is bias error. Second is a precision error. Okay. Now we'll move further. So what is mean by bias error? Okay. Bias means what? We purposefully we go on one side. Okay. Bias means what? We purposefully go on one side. Okay. So, and precision means it is a random type. So what is a bias error? So bias error is also called as systematic error. Bias error is also called as what? Systematic error. Okay. So this type of error occurs each time we take measurement, but in the same way, either plus or minus. It will always be something plus from the actual value, or it will be something plus from the negative value, but it is occurring in the same way. So that's why it is called as systematic error. Okay. So what is the benefit of, we can say, bias error is we can find out it and eliminate it. Okay. So we can find out it. So correction is possible in the systematic, we can say systematic error. Like your instrument scale may consistently read higher value, maybe suppose 5%. Okay. And so entire set of measurement will be biased by 5%. So consistently higher. Okay. So bias error, they are very systematic. So can identify it and we can eliminate it. Okay. So like here 5% offset we can eliminate. Okay. We can eliminate 5% of offset by mechanical mean or some adjustment. Now we'll go for precision error. Precision error is also called as a random error. Precision error is also called as what? A random error. So this type of random error, one time it will be plus, one time it will be negative, one time like that it will be fluctuating. So if you take the average of random error, possibly the average will be 0. Okay. But it occurs either side, and we cannot say that it will occur on plus side or minus side or which side, we don't know. Okay. So what are the reasons for this? What are the reasons for this precision errors? Okay, so it may be friction, it may be vibration, it may be temperature changes. So this can cause the precision error. Okay, so it is not in our hand, we can say. Precision error eliminating is not in our hand because of environment, like mechanical friction, vibration, temperature changes, it occurs. Now I will show you graph here. So here I have plotted what is called as probability density function. Okay, frequency of times it is occurring, and we can see here the spread is can be here 3 sigma plus minus. So this dome is actually representing what is called
Sir,
as,
we can't see dome.
yeah,
We can't see dome.
you cannot see the diagram.
No, sir. Only first PPT we can.
Okay, okay. So I think there is some issue. Okay, I will again share because I was in the another slide. Stop sharing. Can you see now?
Error and error analysis, first slide we can see.
Yeah. So I'll go down. Are you seeing bias error, precision error?
Yes, sir.
Yeah.
Yes, yes.
Now we'll go to this dome. Now here you can see, I'll make a little bit bigger. You can see here the dome. Okay, this dome is actually what it is representing the what is called as precision error. This dome is actually precision error. Okay, we know the bias error, how it is away from the true value, that is a bias error. And plus minus, this will be the plus minus 3 sigma will be the what is called as precision error. Okay, so whenever we write anything, so bias error, it is in our hand to control, but precision error, it is not in our hand. So we have to understand this dome. Plus minus 3 sigma means we have to write x mean plus minus 3 sigma. So that will be our error. Okay, that will be our error. So total error will be bias error plus, we can say, 3 sigma. 3 sigma for the precision error. Okay. So when we want to find the precision error, we need to take a large number of readings. We already learned the statistics, number of readings to calculate, to find the spread. Okay. So we can find the size of this error. Okay. Now we'll move to the detailed study. So we'll see the classifications of error. So basically there are two types of error I have already mentioned. Bias error, we can say it is systematic, and another is a precision error, or it is called as random. Now, what causes each error? We'll see first calibration error. Bias error can be calibration error. There may be some shift, okay? So instrument scale not adjusted to read the measure value accurate. Like I am measuring the 30 degrees Celsius, okay? Actual temperature is 30 degrees Celsius, but it is showing the 35 degrees Celsius. So there in the scale itself, there is a shift. So we can adjust this shift, okay, with the help of calibration. So there is a shift or calibration error. Then certain consistently recurring human errors, like human have some tendencies, okay. Suppose the person is taking the reading in the wrong way, okay, like if you see the rotameter, it is expected you take the reading at the top of the floating bob, okay, but if you are taking at something other level, what will happen? There will be bias error will occur, okay. So we can eliminate this human error by properly training the person, okay. Next is certain errors caused by defective instrument or equipment. So it can be because of incorrect design, fabrication, or maintenance, or defective components. Okay, so we can eliminate it by measuring, correcting the fabrication. Okay, then comes loading error. So what is happening, like when we test something, so it gives loading. Like if you take the case of flow measuring device, okay. So what happens when like if you take the example of measuring the flow, when we measure the flow, what we do, we need to have some holes in the pipe to connect our manometer. When we create these holes, it is also disturbing the flow. Okay, so that is called as a loading effect. Loading effect can give the error. Okay, some error it can cause because locally it will disturb the flow. Okay, so what precaution we need to take when you load the system for measurement? If you take the case of ammeter, you can take the case of ammeter. What is happening in the ammeter? Ammeter will have its own resistance. Okay, so it will affect the system. It will consume some power from the system. Okay, there will be I square R loss in the system. Okay, so this loading should not cause effect on the measurement accuracy. Okay, so it should not kill the what is called as error. Then comes limitation of system resolution. If the resolution is not proper, it will give the error. Okay. Now comes precision error. As we already mentioned, precision error is what random type of error. It can occur randomly. Okay. So this error is not fixed in amount. Please understand. It is fluctuating. It either side plus minus or amount is also varying. So what we see generally, we see the spread. What is the spread? Plus minus 3 sigma we see from measurement. So I already mentioned that precision error is because of environmental factors. Okay, disturbances like friction, temperature changes, mechanical vibration. This lead to what is called as a random error. Okay, so these are the reasons for the random error. So random error, the value is not fixed. It is sometimes becoming positive, sometimes becoming negative, and its range is or the value is also fluctuating. Okay. So what we can do is it is also caused by conducting the experiment as a fluctuating environmental condition. You know that when we conduct the experiment for our setup, like if suppose I use the heater, electric heater by my experiment for heat transfer, what happens to the voltage and current? Our MACB voltage and current, the voltage and current is not fixed. The voltage is not fixed. It goes on fluctuating. So it is also type of, we can say, random error that will give the error in measurement of heat supply to the experiment. Okay. Sometimes what happens, suppose I am conducting the experiment on heat transfer and I am supplying the air to the experimental system, I am measuring the flow, but what is happening to the frequency? Frequency of electric supply, what is called as Z, frequency, it is not 50 hertz, so it is goes on fluctuating. It goes on fluctuating. Okay, so it is not exactly 50 hertz. So if this frequency changes, also the RPM of machine motor will change and it will affect the flow supplied by the compressor or blower or the pump. Okay. Then the error, precision error is also caused by insufficient measurement system sensitivity. So it is not enough sensitive to measure your readings. So all these causes precision, or we can say random error. Okay. So we'll move to the next two errors, that is illegitimate errors, or errors which are mixed bias error or sometimes precision error. So we'll take break, and after 10 minutes we'll come back and continue this topic on the error and error analysis. Okay, thank you.